All right. Welcome back to this 8th class. Crazy to think that our summer semester is 40% done. We only meet for 10 weeks, 20 sessions. This is number 8. Time is flying, and let me not waste any more time by ranting about time flying. You have your usual due dates on the board, quote, board. What a time to be alive. 1.7 is due tonight, 1.8 is the next class, 2.2 the class after that as well. There's nothing super crazy from 2.2 in terms of breadth of material. And while I don't necessarily like having a homework due for a section that's not being tested on yet before the test for the old material, we're in a summer semester. Weird things like that just have to happen sometimes, especially when the test should arguably be on the 16th and I'm giving you the 16th, 17th, and 18th. So there's just some weird things going on. This homework assignment is kind of an outlier. It's unfortunate, but I also don't want to say that this homework's due 2 weeks from now because it's just going to put you behind. Remember, expected time in this class is 8, maybe even 9 hours a week outside of watching the lecture. So that's in addition to the 4 hours you're watching the lectures each week, which is really like, 12, 13 hours a week of investment. That's why they call it full-time schedule, 10 credits in the summer, because 3 classes, that's a full-time workload. 13 times 3, 39, that's 40 hours. Tough to have a full-time job and a full-time course load. Anyways, that review, I'm not even going to pretend like I've built it yet. I've been building the test on yesterday. Once I have the test built, then I will build the review to reflect the test as I promised. I have decided this first test is going to be in my math lab. It's not necessarily the way I wanted to do it, but it's the way I'm going to do it. It's just not worth fighting so many other aspects, at least for now. I did say that we're likely to have a non-MyMathLab test at some point, and I would warn you when that's going to happen. But your review will go to my math lab, your test will go to my math lab. The review grade won't be counted. It will be later. It will be available no later than 5 p.m. today. It will be available the second I finish it, which I don't anticipate taking longer than 3 p.m. to finish building the tests and the review. So if you check back at 3 p.m., you should see the review. You won't see the test until the 16th. It will be hidden until then. But remember, that test will only cover the first 8 sections, and make sure you show your work and upload to Canvas, which there will be a spot. It will be super, super obvious where you're supposed to submit. Submission location to be set on test day. I mean, it's just going to be something that says submit your test 1 work here. You really won't be able to miss it. I don't have that much use of Canvas in that main section anyways, besides the lecture video, some prereq material, and maybe 1 or 2 other things. So if you don't have any questions about that, let us continue on where we left off in 2.2, which when class ended, my Word file crashed. It happens, I would say, almost every day, but maybe every other day that my Word files crash. It doesn't like all the writing and typing. This is an old archaic laptop. Not that y'all care. And maybe that's the reason it's crashing, maybe not, I don't know, but it deleted B, so I just went and wrote it back in really, really quickly. That should look pretty much what it looked like before, but if I'm missing any layer of detail, actually I just realized I didn't show the distribution of the E part. There was another version of the answer that I said was okay, but not great. So I'm okay leaving that off of the screen, but if you want to see it, go to the very end of lecture number 7. All right, so that was example 2. We're going to go to example 3. And we're going to find f prime of 7 if f of x is equal to x times e to the x. So we did a decent amount of experimentation with these exponential rules, and we said that the derivative of e to the x is e to the x, but that is an extremely rare question to be asked. Usually there's other numbers and variables littered all over that because that's just too simple. So we did this with a constant coefficient. It didn't really complicate things. We did one where there was a product, and we got this, and we did one where there was a, did we do a quotient? We did not do a quotient, but we could have certainly done a quotient. And then we did something that involved the chain rule. And we said that the chain rule one has seen so much that we might as well just go ahead and derive a formula for it, which was this, that the derivative of some e to a whatever the exponent is the derivative of the exponent, aka the derivative of the inside, times the derivative of the outside, the derivative of the e part, which is really just itself. So the derivative of an exponential with a more complicated exponent, as long as the base is e, is the derivative of the exponent times the original function. It's just the original function with an extra product. That extra product being the derivative of the exponent. Did a couple examples. Now let's do a third one. Well, I scrolled up intentionally. Because look at this function, f of x equals x times e to the x. That seems, oops, too far. That seems really familiar. So example 1b, we already did this. So we know that the derivative is, and you can use either version you like, it doesn't technically matter. I like the one with e to the x factor. Again, if you have all the terms having the same exponential piece, it is generally better to factor that out. Notice I said generally, not always, generally. So I'm going to use this version of the derivative. I'm not going to reinvent the wheel. I'm not going to do this work a second time. It's already been done. So by example 1, was it B? Ooh, excuse me, that was a rough cough. Yes, f prime of x was equal to e to the x parentheses 1 plus x, right? E to the x parentheses 1 plus x. You could swap the order of the x and the 1. That would be fine. You could use the version where the e to the x was distributed. It doesn't matter. You can redo this whole work if you feel like you need to practice on the product rule. But I need to save some time. So all we gotta do is plug the 7 in. So f prime of 7 is equal to e to the 7 times 1 plus 7, which is e to the 7 times 8, or 8 e to the 7, more appropriately written. Now that is the analytic answer. There is nothing wrong with that. But a lot of people are curious as to what this is approximately. So if you type this in a calculator and round to the nearest whole, 8 second e with an exponent, 7. Close your parentheses, and you get 8773 rounded to the nearest whole. That's the approximation. Please pay attention to my math lab if it wants an exact or an approximate answer. The exact one is what I have boxed up. I'm not even going to box up the 8773. The only reason I would ever care about the 8773 is if this is an application and you wanted a sense of scale to the value. But as a math problem, the 8E7 is more interesting, it's more exact. Okay. What can we do with this? Well, part B, that was supposed to be a part A. Part B, write the equation, you knew where this was going, of a tangent line at x equals 7. 2f of x equals x times e to the x. Well, we have the slope. The 8e to the 7 is the slope. That was the derivative. So by part A, m is the f prime of 7, which was the 8e to the 7. That's the slope. Again, that's the slope. But we need the point. We only have the x value, so we need to find f of x. We need to find f of 7 to get the point. Now we're going back to the original function, not the derivative. F prime and f are different things. So we're just plugging 7s in there, so that will be 7 times e to the 7. So the point is 7 comma 7e to the 7. Lots of 7s. I can't believe I'm going to write this one last time for you. Y minus y1 equals m times x minus x1. There is no reason you should be in calculus if you don't have that memorized. So plug in the point, that was the x1 and the y1. The m was our slope, so we go y minus the y1, which is 7 times e to the 7, is equal to the m, which is 8 e to the 7, parentheses, and then x minus the x1, which is 7. Distribute. You get y minus 7 e to the 7 is equal to 8 e to the 7x minus the 8 times 7 can be multiplied to get 56 e to the 7. And then you can move by adding 7e to the 7 on both sides. And believe it or not, those are like terms. They have the exact same factor of e to the 7. It's like saying negative 56x plus 7x. Just got to do 56 minus 7, which is 49, but it's negative. So you get y equals 8 e to the 7 power times x. So that's the slope and the x. Then a minus 49 e to the 7. And that is the equation of the line. And you might say that doesn't look like a line because of the e to the 7th, but those are just numbers. Again, if you wanted to approximate this, we already know that the 8 e to the 7 is about 8773. So the approximation is y equals 8,773x minus, and this 49 e to the 7, so we got 49 times e to the 7. That's about 53,735. 53735. 53735. Again, that's the approximation. Let me use the squiggly equals for that. The approximation is nice because you can see your rate of growth here, the 8773 per year or month or per day or per whatever the x is measured in. You have your y-intercept here, which says you're starting out at negative 54,000 roughly. So if you produce, maybe this is the model for our revenue if we were to produce X items. So if you make 0 items, our revenue is going to be negative 53, or sorry, profit. I don't know why I said revenue, profit. Maybe you'd profit negative $53,735 because you got to pay your rent and employees even though you didn't make anything. So again, lots of ways that we can then make that more relevant to an application. I'm really focusing much more on the math side of things and the applications in this course, given the nature of delivery. I'm not saying we never do applications. I'm just kind of trimming the fat a little bit as I see necessary so that we can finish the semester in a timely manner. All right, so that is going to close out 2.2. So let's make a new, let's go 2.3, which has a different title than what's on my notes. Derivatives of natural logarithmic functions. Derivatives of natural logarithmic functions. Derivatives of natural logarithmic functions. The natural here is extremely important. Not just a derivative of a regular log. This has to be a natural log. So we will not do derivatives of regular logs in this section. There is a section for taking derivatives of non-natural logs and non-natural exponentials. Back in 2.2, all we did was the natural exponential. What that means is the base was e. There are formulas for things where the base isn't e. There are formulas when it's not a natural log. They're more complicated. They're in a later section, and we will cover that if we have time at the end of the semester. Again, I'm going over the things that we need to cover, and then things that are a little more optional I'm saving for the end to kind of circle back to, because I don't think we're going to have time to circle back to too much. We're already a little behind where I'd like to be as it stands, and I don't think that that's going to get any better. But it is what it is. You'll learn enough to have mastered what you need to master. I can guarantee that. Okay. So once again, in the interest of applied calculus, in the interest of not showing you derivations of calculus formulas because it's nightmare fuel most of the time, we're just going to go straight to brass tacks. The derivative, I don't know why I need that in blue. I'd rather have it in red. The derivative of the natural log of x. That's natural log, ln log natural. But we speak English, so we say natural log because we put adjectives before instead of after. But guess what? English-speaking people did not invent this, so it's log natural. So the derivative of a log natural or of a natural log, which just means its base is e. I'll remind us of that in a minute in writing if you have forgotten that. This derivative is 1 over x. So this is a formula that you must memorize. As I said, calculus is basically a series of memorizing formulas and having mastered pre-calculus material, which means having mastered all the algebra that calculus requires to do. Calculus is a series of formulas and applying them. But in the applications, there's heavy, 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 heavy algebra. So as a reminder, oh, and I forgot to do this. All the little things you got to do. ln of x is a log with a base of e. So ln of x would be the same thing as if I wrote this, log base e of x. Don't ever write things this way. It is technically correct, but you are going to annoy some people a lot by writing log base e of x. Kind of like when you write a coefficient of 1, you're going to annoy someone. When you write an exponent of 1, you're going to annoy someone. It's writing extra things. Why do you want to write log base e when you can just write ln? Also remember that if you have log of x, we assume that the base is 10. Again, you would never write things log base 10, you just write log of x. We're not going to be dealing with this type of logarithm in here unless we get to those extra sections later. We really don't deal with regular logarithms. And the convenience is, and I mentioned this for the exponentials, all exponentials can be kind of massaged into a form of having a base of e. You can take something that had a base of 10 and write it with a base of e, or a base of 7 and write it as a base of e. Same thing with natural logs. You can take a natural log of any base and turn it into another base using the change of base formula back from pre-calc 1. But we're going to practice the calculus of things. This is not pre-calc 1. We've done that stuff already. You should have done that stuff already. So, calculus. Example 1. Find f prime of x or y prime given f of x or y. Let's have f of x be 5 times the natural log of x. Okay, so the formula, again, is right here. Got to have it memorized. This just has a coefficient in front of the thing we're taking a derivative of that we just discussed. So coefficients don't really have an effect on it. You're just going to put the 5 in front of your answer. So f prime of x, leave the 5 alone. Then the derivative of the natural log of x is 1 over x. So that's 5 times 1 over x. But no one's going to leave things as 5 times 1 over x. You're going to multiply the 5 and the 1 because they both count as tops. So that's our derivative. The 5 and the x did not multiply. The 5 and the 1 are in tops. Remember, if you need to write this as 5 over 1, you can, but most people generally don't do that. B. F of x equals x squared times the natural log of x. Well, in A, we had the 5 times the thing. Now we've got x squared times the thing. We know the derivative of the thing, it's 1 over x. Now when it was just a constant coefficient, that doesn't have an effect. This is not a constant coefficient. This is a variable, if you will, coefficient. Product rule is necessary. Which, just using my first and seconds, I will write out again as the second times the derivative of the first plus the first times the derivative of the second. There's lots of versions of that. You know, I've said that 50 times by now. You better master it by test 1. And actually, before I go writing all that, let's write what first and second are. So what's the first thing? That's the x squared. What's the second thing? That's the natural log of the x. What's the derivative of the first thing? That's a power rule. Bring the 2 out front, decrease the exponent by 1. So 2x. What's the derivative of the second thing? We were literally just told it's 1 over x. Leap of faith, I know, but take the leap with me, please. It is 1 over x. And there's some fascinating details about that derivative that aren't necessarily true. And when you go with that backwards thing I've kind of talked about, you end up needing kind of more detail in here. The only thing I want to point out that's weird about this is that the natural log function is only defined for positive x values, but its derivative is defined for all values. So this is a slight misnomer. You have to have x being positive. So what some people like to do is then say, come back here and say, note, x has to be bigger than 0. Because you can't take the natural log of a non-positive, you have to restrict the x and the derivative to be the same. You can't let the x be negative in its derivative when it wasn't allowed in the main function. If there's a portion of the domain that doesn't work for the regular function, it's not going to work in the derivative either. Now, we don't get super analytical in this course, so it's not as big of a deal, but I do like to at least point out that you're only supposed to be dealing with positive x's for this statement to be exactly accurate. Okay, back to the problem at hand. We have our product, so we labeled a first and a second. We took each of those derivatives independently. Now we can say that f prime of x. And again, with the product rule, just make sure you're taking a regular thing times a derivative. You're mixing your first and your seconds and you're adding. But again, I like this pattern because it's consistent with the quotient rule in terms of the order that the derivative of the first is in the first spot, the derivative of the second is in the second spot. All right, so second times derivative of the first. That's these two. So the second is the natural log of x times, there's our 2x. Now you got to be careful here. Don't multiply the x and the 2x. The x is inside a natural log, the 2x is not. You can't multiply them. What some people like to do is go back and wrap the natural log in parentheses to emphasize that, in fact. Again, you cannot multiply the x and the 2x because they're in and out. It's kind of like if you have a square root of x times an x. You have an x outside and an x inside. They can't communicate. So now we're doing the first times the derivative of the second. That's this pair. That's the x squared and the 1 over x. So that's plus 1 over x squared. There's our first times, excuse me, not 1 over x squared. I'm reading and writing at the same time. The first is x squared times the derivative of the second is 1 over x. So because it can lead to confusion writing things this way without the parentheses, it is really best to ultimately put that 2x in front of the natural log. That's the better way to write that first term. Then plus, you have an x squared in a top, an x in a bottom. You're going to lose an x from top and bottom. If you had 2 of them in the top, that's going to go down to 1. If you had 1 in the bottom, that goes down to nothing. So again, that's x squared over x. You cancel the 1 in the bottom, the 2 becomes a 1 in the top. That's x to the first over 1, which is just x. So this is our derivative. C. Let's have y equals, let's change up our notation, to the natural log of 5x. I like to do my notes in kind of a specific way that there's patterns. When we were doing the exponential section, we did a 5 e to the x, then we did an e to the 5x, and we saw with the 5 e to the x, that coefficient did nothing really, just got brought along. But when you had the 5 inside, it was a chain rule. Guess what I'm trying to emphasize between A and C here? The 5 outside really did nothing, so it just ended up multiplying by the derivative of the more important chunk. Whereas here, that 5 is inside, so guess what? We need the chain rule. Spoiler alerts, this gets used so much that we're going to go ahead and write a second logarithm definition for a derivative for the chain rule, so you don't have to think about the chain rule every time. But before we get that far, all right, so we need to label an inside and an outside. Well, the inside would be the 5x. The outside would be the natural log of, and again, I like emphasis here. This isn't really an x. This x is that u, it represents the inside. So please note that the blue x is really the original inside. So remember, the chain rule says f prime of x would be the derivative of the inside times the derivative of the outside. Derivative of the inside times the derivative of the outside. So we need to take these derivatives. The derivative of the inside is 5, because that's a linear term. That's one of the special cases. The derivative of the outside, well, the derivative of the natural log of x is 1 over x, but that x is special, so it's 1 over what really means the inside. So y prime, because this wasn't an f, it was a y, or you could write dy over dx. It's going to be the derivative of the inside, which is the 5, times the derivative of the outside, which is the 1 over x. But it's that 1 over the special x, which you may write as a u if you prefer. That represents what the inside is. So this blue x, I don't write x, I write 5x. Because again, this right here is the same thing as this. Well, here's what's interesting with this problem. There's a 5 in the top and a 5 on the bottom. The 5s cancel. And we get that the derivative is 1 over x. Huh, interesting. It's the same as without the 5. Now, I will point out something critical. This is not always the case. It depends on the complexity of the function. It depends on the complexity of the function. Back in pre-calculus, we saw some functions that their inverses were the original function, and that was kind of fascinating. And in fact, 1 over x is one of those. Now, what we're doing here has nothing to do with inverse functions, but what I think is fascinating is that the derivative of the natural log of 5x is the same as the derivative of 5 times the natural log of x. What's interesting here is a coefficient inside of a logarithm does not affect the rate of change. Rate of change means growth. It means its slope. I'm just saying this is interesting because when we had the 5 outside, it did affect its rate of change. The derivative was 5 over x instead of 1 over x. It's growing 5 times as fast. If I put a 7 here, it would be growing at the same rate. If I put a million here, the natural log of a million x, it would be growing at the exact same rate as if I just had a natural log of x. Now, if there's other variables in there, if there's an x squared or a 7x or an x to the 5th or anything like that, that's much more complicated and it does affect the change. But a constant inside of a natural logarithm doesn't actually affect the rate of change. It doesn't affect the slope. Now, I'm not saying that chain rules are completely unnecessary. I had never said that. Again, I'm trying to emphasize this is kind of just a special case. Chain rule has to be done even with these simple problems because you can make mistakes otherwise, especially with the more complicated ones. So let's lay out what the chain rule for natural logs is. So we can skip labeling the insides and the outsides for this because, again, it's a pretty common occurrence. So the derivative of the natural log of a function. So in other words, the natural log of something besides just an x. So this could be a 5x, it could be an x squared, it could be a million x minus 7. What it turns out to be is the derivative of the inside divided by the inside. This is fascinating. And the previous example does actually demonstrate that. This 5 was the derivative of the inside, and the 5 ends up in the top. The bottom, the 5x, was the original inside. Again, the top, the 5, that's the derivative of the inside, which again, I wrote it to the side, but that can be considered to be in the top. The bottom, the 5x, was the original inside. So that's what this says. The derivative of the inside divided by the inside. This is equal to, again, the derivative of the inside divided by the inside. That's using our words. This is using our math. This is using our words. So let's try using that on a more complicated problem. So for example 2, let's find f prime of x, and you know what? Let's put it down here. I almost wish there were no page breaks the way I'm doing things. And this is going to be f of x, and this is a. F of x equals the natural log of x to the third plus 2 in parentheses. Definitely getting into the more complicated functions. Now, you can still apply the chain rule as we did with the previous example. You can label the inside, you can label the outside, you can label the derivative of the inside, the derivative of the outside, and do all that appropriate stuff. Or instead, again, because we see this so much, so very, very, very much, you can just say, let me memorize this extra formula. The derivative of the natural log of something else, let's call this the inside, is the derivative of the inside divided by the inside. Get these in order. If you swap them, it's wrong. If you do the inside divided by its derivative, wrong. It's the derivative of the inside divided by the inside. So I'm just gonna, I will label what the inside is. Oops, wrong color. That's x cubed plus 2. I'll even write out what the derivative of the inside is, which would be 3x squared. The derivative of x cubed is 3x squared. The derivative of 2 is nothing. That's what, the 100th time we've done the power rule together, probably? So that says f prime of x is equal to the derivative of the inside divided by the inside. The derivative of the inside is the 3x squared divided by the actual inside was the x cubed plus 2, and guess what? There's literally nothing we can do to that to simplify it. That's it. That's all we have to do now. We don't have to label the outside with some confusing substituted variable, whether we're using u or a different x. It's a lot nicer this way. The same reason we gave an abbreviated chain rule formula for exponentials with a base of e. But with just plain Jane polynomial and product and quotient functions, we can't label a general chain rule for every single thing like that. We'd have to memorize 5 million formulas. So we don't. Alrighty, another one, B. We'll do two more. F of x equals the natural log of x squared plus 5 raised to the 4th power. Now I need you to note this is not the natural log of x squared plus 5 raised to the 4th power. If you need to see extra brackets and things, it's really the natural log of x squared plus 5 in parentheses to the 4th power. In other words, the exponent of 4 is inside the natural log when written this way, not outside. That is a giant distinction, because if we had to do the problem that it's not, this would be a double chain rule, which we have done before and you can do, but that's not what this is. This is a single chain rule. So if you want to call the inside something, it's the x squared plus 5 all raised to the 4th power. Then the derivative of the inside, well, you got to chain rule this. So the derivative of the outside is going to be this. I'm going to do this a little quicker. It's 4 times the inside, and then drop the exponent by 1. This right here is the derivative of the outside, pretending that the inside was just an x. Again, this was the derivative of the outside times the derivative of the inside being the x squared plus 5. I will go back and show all the detail. I'm just showing a quicker way to do this thing. So this is me. Everything that I'm scribbling out right now is what I'm calling the inside. I'm pretending like that's just a single x when I do my derivative of the outside. So I'm pretending that it was x to the 4th, and its derivative is 4x cubed. But then I got to do times the derivative of the inside. Well, the inside was x squared plus 5, which is a derivative of 2x. The derivative of the 5 is 0. Now that is really the 4 and the 2x can be multiplied to be 8x times x squared plus 5 raised to the 3rd power. So we got our inside and we got our derivative of our inside. So that means we can write our f prime of x. It's just the ratio of those two things. It's the derivative of the inside divided by the inside. The derivative of the inside is what goes on the top. That's the 8x parentheses x squared plus 5 to the 3rd. If you need to see that derivative, I'll do that at the end in more detail. Divided by the inside, that was the thing to the 4th power, the parentheses x squared plus 5 raised to the 4th. Now here's what's fascinating. You have like terms that can cancel. You have common factors, not like terms, common factors. X squared plus 5, x squared plus 5, so we can get rid of some of them. There's 3 in the top, there's 4 in the bottom, so we can cancel 3 of them. So we can get rid of 3 of the 4 in the bottom, which means there's 1 left over. We can get rid of all 3 in the top, which means there's 0 left over. So f prime of x is the 8x is still on the top. The parentheses is completely gone in the top, but you still have your x squared plus 5 in the bottom. So that one I think is fascinating because this exponent that was a 4 was completely irrelevant. It makes this chaining much more complicated when you do the derivatives this way. But after you get your derivative, the derivative of the inside over the derivative, over the inside, derivative of the inside over the inside, you end up canceling out almost all of them except for just a single one in the bottom. I'm going to show you, excuse me, I'm going to show you using a pre-calculus rule for logarithms why this works even without chaining anything. But before that, I said I would point this out in writing. Note, for x squared plus 5 raised to the 4th, its inside is x squared plus 5. Its outside would be that special x raised to the 4th power. Again, where that green x really represents the inside. So the derivative of the actual inside is 2x. The derivative of the outside would be the 4x cubed with that special x really representing the inside. So its derivative, let me just call it y prime, if I call that y. The derivative of the inside times the derivative of the outside. So that's 2x times the 4x cubed, but it's not really 4x cubed. It's that parentheses x squared plus 5 cubed. Which is really 8x times x squared plus 5 to the 3rd. So that says what we got above, whether we do it a short way or a long way. But when you've done 20 or 30 or 40 chain rules, you should be able to get much more efficient with them when they're just a polynomial raised to a power. Practice makes perfect. If you do 5 of these, you're probably not going to feel comfortable on a test. If you do 30 of these, you're going to feel much more comfortable. That's why we tell you study this stuff for 8 to 9 hours a week outside of class. You include class time, that's 12 to 13 hours a week that you should be doing this. Okay. Before we move on to another example, I said I would show you another way to get this derivative without chaining it. This 4 right here doesn't need to be an exponent. So let's go back to pre-calculus. Back in pre-calc, you learned that the log of anything with an exponent, where the exponent's inside the log, can just be brought out as a coefficient. The exponent can be brought out as a coefficient. The exponent becomes a coefficient. This is only for logarithms. Any type of logarithm works, but it's only for logarithms. That's never true of anything else in the world. The exponent inside of a logarithm can become a coefficient outside of a logarithm. There's reasons that works. We're not going to prove it. This was pre-calculus. You should still remember this. You could still need this at some point in this course. So let's go back to the original function, which was the natural log of x squared plus 5 to the 4th. Check this out. Using that rule, you can bring the exponent of a 4 out front to go 4 natural log of x squared plus 5. Now you can't do the same thing with this exponent. You can't do that with the 2 because the whole thing isn't being squared. It's just a single term. Well, guess what? Now that 4 is just a coefficient, it makes this derivative a lot easier to take. It's just derivative of the inside divided by the inside. So f prime of x be 4 times the derivative of the inside over the inside. which is 4 times the derivative of x squared plus 5 is 2x, over the actual inside is x squared plus 5. The 4 times the 2x makes 8x over x squared plus 5. Same answer. Much easier that way, but if you don't remember that pre-calc rule, it wouldn't give you efficiency. Did you need that rule to do the calculus? No. Does it help you do it more efficiently? Yes. But at least that shows that the calculus that we did with all the extra chain rule stuff, it wasn't for naught. It actually works. It's nice when we can get an answer a separate way to say, yeah, okay, that's good. If it's right 2 different ways, it probably makes sense. All right. And that was B. So let's do C. Last problem for the section. F of x equals the natural log of x to the 4th plus 1, then a minus 4, that's an ugly 4, e to the x over 2 minus x. Multiple terms, so at least with the pluses and minuses, they don't affect each other for derivatives. But we gotta take a derivative of a logarithm with a fancy inside, so we're gonna need its particular chain rule. We gotta take the derivative of a fancy exponential, so we're gonna need its particular chain rule. And we got a derivative of a polynomial, so we need to know that in all its special cases. So for the first bit, for the natural log of x, its inside, sorry, the natural log, I didn't mean to say x. Its inside is the x to the 4th plus 1, and its derivative would then be 4x cubed, because the derivative of 1 is 0. I'll do this in a different color. For the exponential, the inside is the x over 2, and its derivative would be 1/2. X over 2 is a linear term. It's 1/2 times x. And the derivative of a linear term is its coefficient. We don't need any fancy stuff for the minus x part. So f prime of x equals, for the natural log part, that formula was the derivative of the inside divided by the inside. The derivative of the inside divided by the inside. The derivative of the inside divided by the inside. So let's go back to our red. The derivative of the inside was the 4x to the 3rd over. The actual inside was the x to the 4th plus 1. Then the minus. That 4 is a coefficient, leave it alone. The exponential rule said that the derivative of an e to something fancy is the derivative of the inside times the original exponential. The derivative of the inside times the original exponential. So the derivative of the inside is that 1/2. Times 1/2, that's the derivative of the inside, times the original exponential, that's the e to the x over 2. Then minus, the derivative of x is 1, so minus 1. Again, linear term, special case. Let's clean this up and write it all in the same color for sanity's sake. Nothing you can do to the first bit, because the bottom's a binomial. Why did I say monomial? The 4 times 1/2 is 2, so that's minus 2e to the x over 2, and then a minus 1. That's all we can do. You can do this stuff with a product of an exponential and a logarithm. You can do it with quotients. Everything can be combined. With derivatives, any and everything can always be combined. It's just a matter of what the nature of the problem is, what they want to give you. All right. So that is it for chapter 2 for now. We will come back to it if we can at the end of the semester to talk about some more interesting topics, or if I find that we're on a really good pace before we get to integration, I would prefer to come back to this topic, but I usually can't gauge it at that point. Some semesters I've been able to come back to it, some I haven't. It really does just depend on how far we can get in the class. But the crazier topics I would rather save for the end. I want to make sure we can get the core concepts down. Because if you've got the core concepts down, if you then have to apply it into some 300 level economics class, they're going to give you the applications. You just got to know your calculus formulas and how to apply them. So you generally would see this stuff again in terms of applications, unless you just have a teacher who's going really quickly through stuff. I don't know. So that'll be it for chapter 2 temporarily. I hope that I can save this later. So what we get into now is chapter 3. And yes, we do have to keep moving forward. We can't waste time. Remember, test 2 is going to include several different chapters. It's going to be parts of chapter 2, parts of chapter 3. That should be it, just parts of chapter 2 and parts of 3. We don't need to talk about that too much for a while. So 3.1, using first derivatives, classify maximum and minimum values, sketching graphs. Ourselves lots of space. Okay, so we have now got a series of formulas for finding derivatives. We can find the derivatives of several different classes of functions. We know how to find derivatives polynomials using the power rule, products and quotients, composite functions, that was the chain rule, and then natural exponentials and natural logs. Yes, I want my Oxford comma. I am an Oxford comma person. Which some people probably say that it makes me evil or something like that. I think it just means I like commas. So that's what we've done in chapter 2. We have learned, chapter 1 and 2, chapters 1 and 2. In chapter 1, we picked up polynomials, product, quotient, and composite. Just that brief synopsis in chapter 2, we picked up the natural exponentials and the natural logs. Once again, if this was a true calculus course, we would need a whole other series of derivatives. We would definitely need the general exponential and general logarithmic derivative. We would need derivatives of trigonometric functions. We would need derivatives of hyperbolic functions, which some pre-calc classes don't even get into what a hyperbolic function is, so that can be kind of jarring. And I'm not going to get into that because that's not what we talk about in here. So that's what we have so far. We are able to find derivatives of all the classes of functions that we need to be able to take derivatives of. So what we're going to start doing to expand this concept of calculus is some very deep graphical analysis. And you started doing graph analysis back in Math 161. We talked about finding maxima and minima just by having a graph and pointing and saying, hey, this is a max, this is a min. So back in pre-calc, you could make a graph or be given a graph and find its local extrema which were the local maxima, local minima, which just means highest and lowest points in a region, by looking for peaks and valleys. So back in pre-calc 1, you got some graph. And it looks like this. And we could say that there is a local max right there and a local min right there. Those are our peaks of our hills and the bottoms of our valleys. We can't say they're absolute extrema, which would mean the highest and lowest values, because this curve goes up forever and it goes down forever. So there's lower and there's higher points. But what we're talking about here is you're imagining that you're only looking at the window right around here. So for any particular point, imagine you took your nose and you put it on that little blue dot right there. And when you look at that, you would see in the area around it, everything else is below it. So in that green little spot, let me zoom in. If you were to zoom into that spot, all you'll see is this. That's all you would see. And in that local region, in that small region, it is the highest point. But it doesn't say it's an absolute max, it just says it's a local max. Another word for local is relative, by the way, and I'll write all that out. The same thing would be said if you did that here. If I did it here, if I zoom in here, then the graph is just doing this. I don't see any peak or valley there. That's why we're only looking for sections for tops of hills or bottoms of valleys back in pre-calc 1, and then we just hope that we have those coordinates, either by plugging an x value into the function or whatnot. But that was us using visual aids. In calculus, our idea is not to necessarily look at this, but to find exactly where this is located by talking about how the slope changes. So in calculus, we find these not necessarily by just visual observation, but by discussing how the function is changing, because at these points, the change is very specific. Okay, so definitions, local extrema, aka relative extrema. Just in case your pre-calc's rusty, a relative maximum, sorry if I'm saying a, let me pluralize it actually. Sorry for that. Relative maxima are the highest points in a small region. Relative minima are the lowest points in a small region. Again, when I say small, I mean very small. You imagine that you are taking your nose and you're putting it on a peak or a valley so that all you can see is just that teeny, teeny, teeny little section around it. You're putting on your blindfold, if you will. That was my knuckles popping. Bones and joints, which I'm sure you heard. So that's what we mean by local extrema or relative extrema. There can be multiple local maxima. There can be multiple local minima. So I don't want that highlighter green color anymore. So our curve could do something like this. And then it's got a whole bunch of different, I'll do in blue, the local maxima. And then in, let's go with orange, the minima. So minimum is singular, minima is plural. When you have that A at the end, that's plural. So there's 4 local maxima here and 3 local minima here. There is actually an absolute max, which means the highest of the highest points. And the way I've drawn it, it kind of looks like this one. But there is no absolute min because this graph points down in both directions. And we'll get into absolute extrema later, but not yet. So using calculus, what can we say all of these things have in common? Well, I'm hinting at what we should be thinking about. We should think about how they're changing. How are they changing at these peaks and valleys? So let's zoom in. Let's go back to the zoomed in feature of just some of these. Let's look at the first one originally. Oops, and I don't want to write. Let's zoom in on the first graph to the 2 peaks, the 2 extrema, excuse me, the peak and the valley. So the green one I'll keep as a green box. And then the other one I'll just do as a different colored box. Let's go with gray. So again, nose to the board. And you don't even have to zoom in though, but I just want to try and emphasize this. So we got our gray box. And in that region, the curve was doing this. And we are very interested in specifically the peak and the valley. So here's the curve. There's what it's doing in those 2 different sections. So calculus, study of change. Well, when we were talking about curves, very often we talked about doing tangent lines. So let's zoom in on the first 2 graphs and make tangent lines. So in red, I'll do the tangent lines. Well, at this point, the tangent line is doing this. At this point, the tangent line is doing this. Those tangent lines have a very specific slope. You should all know exactly what that slope is. There's no excuse not to. You're calculus students, right? The slope of a horizontal line is not undefined, it's 0. And that's for both. That's what they have in common. Now, if you look anywhere else in the curve, if you look right here, its tangent line looks like this. If you look right here, its tangent line looks like that. If you look right here, its tangent line is like this. They're non-zero. That is what these values have in common. So what do they have in common? The slopes are 0 at the maxes and the mins. Asterisks, they can also be undefined in special cases, so we'll throw that into the mix as well. But you can just say both slopes, i.e. derivatives, are 0. Note, undefined can be seen rarely as well. We don't really get into that condition too often, but I will throw it into the instructions on how we can do this. All right, so the slope is 0. That's the entire backbone of what we're about to do for finding critical numbers. Actually, let me not say it that way. To find all relative extrema. We'll get to the critical number part in a bit. First, find f prime of x. Why are we finding f prime of x? Because we need to talk about their slopes, and derivatives are slopes. Second, find the critical numbers, which are the x values where f prime of x is either 0 or undefined. If you're dealing with polynomials, the undefined part isn't an issue. If you're dealing with rational functions, then it is. Polynomials can't be undefined. You should know that by now. Rational functions can. So with these rational functions, under rare circumstances, you can get extrema when there's an undefined section. It's not typically seen, but it can happen. All right, third. Remember how in Pre-Calc 1 we did test points for talking about increasing and decreasing, things like that? Well, we're going to go back to that basis. Use test points to the left and right of each critical number. Maxima occur. I don't want to tab that actually. So this is just an extension of the third step. We're still in the third step here. Maxima occur if f prime of x, if the derivative is positive on the left and negative on the right. The critical number. Vice versa, minima occur if the derivative, I can type, I swear, is negative on the left and the derivative is positive on the right of the critical number. This is called the first derivative test. This is known as the first derivative test. The reason we call it the first derivative test is because we're using the first derivative to test out what happens. There's also a second derivative test, spoilers. Guess what you used for that one? We'll talk about that another day. So the greater than 0 and the less than 0 part, that's just saying positive or negative. So if you wanted to just abbreviate things, if the derivative is positive on the left and negative on the right, or if it's negative on the left or positive on the right. Now that memorization seems very random at first. And guess what your teacher did? Your teacher never memorized it that way. Nope. I love pictures. A picture is worth 1,000 words. Now, if you were going to memorize it that way, if you can get it, that's fine. Let's use pictures to figure this out. So on the left, I'm going to draw an upward-facing parabola. And I'm going to have a little point right here, which would be the min. We can tell it's a min because we're looking at it, it's the lowest point. Now let us paint some tangent lines. At this point right here, that slope is negative. This point right here would also be negative. All of these points would be negative. I'm sorry, all of the slopes at these points would be negative. Every tangent line drawn here would all have negative slopes. Let me in fact, without doing the dashes, I much prefer the dashes, but I'm going to have to do it this way so I can erase. Here's a tangent line right here. Its slope is negative. Let me do another one. Let's get a little closer. Here's the tangent line right here. Guess what? Its slope is negative. if I go extremely close to it, right here, it's going to be practically flat, but that tangent line would still be negative. On the left side of this thing, on the left, all tangent lines are negative to the left. So I'm kind of splitting this thing in half. That's awful. I'm visually splitting this thing in half. I'm thinking about tangent lines on the left. Now this tangent line, that slope might be -1. As I get closer and closer, it's going to go to 0. It might be -1/2, then -1/3, then 0. Maybe it's 5, 4, 3, 2, 1, 0. -5, -4, -3, -2, -1, 0. But on the right, I'll do these tangent lines in blue. Here's a tangent line right here, and that one's positive. It's probably something like 4. And then let me get closer. This one is a little flatter. It's probably like 3, but it's still positive. Let me get closer. This slope is still positive, but it's smaller, so it's probably something like 2. Let me get super close. This one is practically flat, but it's still positive. It's probably like 1 or 1/2 or 1/3. But every single tangent line on the right, all of them have to be positive because it's going down and then it's going up. It's decreasing and then it's increasing. So if it's decreasing, that means the slope is negative. If it's increasing, the slope is positive. Again, if you're decreasing, the slope is negative. If you're increasing, the slope is positive. The first derivative tells us all these things if you look at certain x values. But specifically at 0, that tangent line has a slope of 0. So I like this picture, decreasing, increasing. The slope is negative, slope is positive. That is how I know I've got a local minimum. If it goes down, then comes up. So again, down, up. Your m is negative on the left, and it's positive on the right, which makes that a minimum. Flip the script, draw a downward parabola. So this point has to be a max. You get the same argument. I'm not going to draw the 50 lines this time. Now on the left side, all of your tangent lines are positive slopes. On the right, all of your tangent lines are negative slope, and the closer you get to that point, the more it goes towards 0. And at that point, it is always exactly 0. Oops, why did I draw the downward again? There we go. So when you have a max, your slope goes from negative to positive around it. So for the test point stuff, what you do is you find the critical numbers, which are your potential extrema, your potential mins or max. So when you set your derivatives equal to 0 or undefined, which still involves a 0, we'll see one later. When you do that, you're finding it could be a maximum, it could be a minimum, you don't know yet. To find out whether it's a max or min, you're going to plug in x values surrounding the critical numbers and find out whether the derivative is positive or negative. If it goes positive then negative, it means it's going up then down, so it's a max. If it goes negative then positive, it means it goes, I wrote these backwards. I wrote this backwards. Shoot. Right here, this was supposed to be the positive, this was supposed to be the negative. I'm sorry. You're positive on the left, negative on the right. If you're decreasing then increasing, if it's negative then positive, it's a minimum. If it's increasing then decreasing, then it's a maximum. You are not plugging function values, you're not testing function values, you're testing derivative values because you need to be observing the slopes. All right, so paired with this, we can draw graphs of functions by plotting the extrema first and bending to them appropriately, in addition to using the leading coefficient test if needed. So that's a pre-calc technique. You can dust off that. It's based on whether the leading coefficient is positive or negative, and it's also based on the degree of the polynomial, whether the ends both go up, both go down, or a mix and match. I'm not saying you have to do that. Back in pre-calc, we used the leading coefficient test. We found all the zeros, and we would make sketches based on that. So I'm going to erase this in a second, but back in pre-calc, you would say like, all right, the ends go up and up. Oh, well, somebody said something.
Look at the matches what I'm about to bring to your house. I'm about to bring these to your house, Mommy.
Oh, okay. What are markers?
If you could turn your mic off, that would be great. Appreciate it. Thank you very much. And hi to your youngin as well. I hope they're learning some calculus. So back in 161 or pre-calc, you would plot zeros and all your intercepts and stuff, and then you would have multiplicities, and you'd say, all right, well, I know I'm going to bounce on this one, and I know I'm going to bounce on this one or cross on this one, and you would make your graphs based off of that idea. But then you'd have these little peaks right here that you couldn't necessarily find the height of. No sweat there. You had these peaks and valleys that you couldn't necessarily find the height of because you didn't know exactly what x value they occurred at. And if you can't find the x value, you can't find the y value without just pulling out a calculator and going, there it is. Calculus, we don't really focus on finding the zeros as much, more so we focus on finding the peaks and valleys, because we tend to relate this to production, and you like producing at maximum outputs or maximum profits. So you want to be at the peaks, or maybe you want to minimize your losses or minimize your expenses. So that was the pre-calc way. In calculus, what we go through and we do, and we find the extrema. So we'd say this was a max and this was a min maybe. And since this is a max, we know we point down from there. Since this is a min, we know we point up from there. And then you just go through and connect the dots. So I don't know why I did that. That was just a sleight of hand. So you do that, you connect there, you make them bend like normal polynomials. It's just a different graphing approach. And I'm not saying we can't find the zeros as well. We certainly could. They might be difficult to find, but the potential is there. So we're going to try graphing some lines in this respect. Example 1. Graph the function by finding critical numbers, identifying the specific extrema, and behavior if needed. And our function, f of x, is going to be x cubed minus 12x squared minus 60x plus 36. So there's our function. Now I'm not pulling out a graphing calculator for this until the very end. Until the very, very, very end. So this is calculus class. Calculus is derivatives and integrals later. We should probably be doing a derivative. Yeah, that's what I said. We want to find the extrema. To find the extrema, we need to know where the derivative 0 or undefined. Derivative, this is a polynomial, so we're going to just power rule everything. So f prime of x. The derivative of x cubed would be 3x squared. You should be able to rocket through these by now in this chapter. Minus, drop the 2 out front. 2 times 12 is 24. Decrease the exponent by 1, so that's a 24x to the first, which again, I don't like writing the 1. Kind of makes it look like a derivative. Then minus, the derivative of 60x is 60 because that's a special case of the power rule. The derivative of 36 is 0. So there is our derivative. Now this is a polynomial. It can't be undefined. So we only set it equal to 0. You can't set a function equal to undefined. There's another thing that you'll do that we'll talk about later. But just remember that polynomials are defined everywhere. We're going to set this equal to 0 to find our critical numbers. As we said, at all of those peaks and valleys, their tangent lines are always horizontal. So we set the derivative equal to 0. We've done our calculus. The rest is algebra. To set this equal to 0, well, it's got an x squared, so factoring is going to be involved. There is a GCF of 3 that you should take out first to make things easier, to make the factoring easier. So that's x squared minus 8x minus, what's that, 20. So that 0 equals that. Factor pairs of 20 that subtract to 8, well, we got 1 times 20. That's 19, so that doesn't work. 2 times 10, well, that difference is 8, so that's going to be it. 4 times 5 would have a sum of 9. We're supposed to be taking a difference, so that's obviously wrong. So we go 0 equals 3 parentheses, x 2, x 10. 2 times 10 is 20, 10 minus 2 is 8. We got to make sure that comes out to a negative 8, so it's a positive 2 and a negative 10. Your signed arithmetic skills have to be on point. Your factoring needs to be on point. If you can't factor, calculus is going to be difficult. To set each of these equal to 0, we've got 3 equations. We set 3 equal to 0. Then we set x plus 2 equal to 0. Then we set x minus 10 equal to 0. 3 equals 0 is trash. 3 is not 0, so we throw it away. Subtract 2 on both sides and you'll get x equals negative 2 for the second equation. Add 10 to both sides and you'll get x equals positive 10 from the third one. These are our critical numbers, negative 2 and positive 10. These are the locations of our extrema. We don't know if they're maxes or mins yet. They also can be neither. Some critical numbers turn out to be neither a max or a min. The specific condition is we need to see this thing decreasing on the left and increasing on the right to be a min, or increasing on the left and decreasing on the right to be a max. Which again, when I say increasing and decreasing, that means positive and negative derivatives, positive and negative slopes. So now we need to test around these critical numbers in the derivative, not the function. The function doesn't talk about how it's changing. The derivative talks about how it's changing. So here's what I like to do. Come on, give me my other color. Ah, boy. Oh, there it is. Okay. I like to draw a little number line kind of thing. And let's put the critical numbers up there, the negative 2 and the 10, in appropriate spots. So negative 2 would be over here. This was a critical number. And then 10 would be over here. This was a critical number. There are 3 regions. There's the region to the left of negative 2. There's the region between them, and the region to the right. Let us use numbers to the left, middle, and right of those. So I'm going to use -3 as a test point. I'm going to use 0 as a test point, and I'm going to use 11 as a test point. Are those the three values you have to use? Absolutely not. I could have used -4 instead of -3. I could have used -100 instead of -3. I could use -2.1. As long as your test point is something to the left of -2, then you also have one between -2 and 10. 0 is the most convenient number. And then one to the right of 10. 11 is pretty convenient. 12 would be good. 15 is okay. 20, you're getting too big at that point. But every student could do different test points and still make an accurate analysis. It's not about the number. It's about being a number in the right region for all three of them. So we are going to plug the -3, the 0, and the 11 into f prime of x. All we care about for the outputs is whether they're positive or negative. We only care if the answers are positive or negative. That's all we care about. So I'm going to leave some space up here to come back to. So f prime of -3. Now, our derivative was the 3x squared minus the 24x minus 60. You can certainly use this version, but it's easier to use the factored version. It's easiest to use the factored version. EASY. So 3 times -3 plus 2 times -3 minus 10. I'm plugging it in here. I'm saying that's the easiest version, but it's not 0 equals. It's going back to the original f prime of x. You will get the same answer if you plugged it into 3x squared minus 24x minus 60, but here I don't need to know what the numbers are. I just need to know whether each piece is positive or negative. So f prime of -3, 3 is a positive, -3 plus 2, that's times a negative, times -3 minus 10 is a negative. A positive times a negative is a positive. Because the two negatives cancel. That's all I care about. I don't care that this is 3 times -1 times -13, which is -3 times -13, which would be positive 39. I don't care that it's positive 39. I only care that it's positive, which means the slope is positive. It's increasing. It's going up. I actually didn't leave enough room here, so I'm just going to redraw it after the fact. So to the left of our critical number, we're increasing. Let's come back to that later. Now let's do the middle one. F prime of 0, that's 3 times 0 plus 2 times 0 minus 10, which is, sorry, not 3, positive. Did not mean to hit that. Please don't crash. And it crashed. How much did we lose? Not much. Good. It's not going to let me undo that, so I just got to erase. Okay, positive. The 0 plus 2 is positive. The 0 minus 10 is positive. Positive times a positive times a positive is a positive, and I'm positive on that positive fact. Can anyone catch my error? I did that intentionally. 0 minus 10 is not positive. It's negative. Positive, positive, negative. So f prime of 0 is not positive. Positive times a positive times a negative is a negative. So that can very easily happen. You got to be careful. A lot of people just get in the, oh, positive, positive, the last one's positive. No, be very careful. Watch your signed arithmetic. It makes a big difference. So because the derivative at 0 is negative, that means the slope is negative. It means it's decreasing. Now let's do the 11. We're not plugging in the critical numbers. I'm not plugging in -2 and 10. Guess what the answer is if you plug -2 and 10 in? It's 0. We know that because we found those values by setting the derivative equal to 0. All right, so f prime of 11, this will be 3 times 11 plus 2 times 11 minus 10. 3 is positive, 11 plus 2 is positive, 11 minus 10 is positive, and this, excuse me, the derivative at 11, that one is positive, no mistakes made. So therefore your slope is positive, it's increasing again. This graph goes from decreasing to increasing to decreasing. We did this type of analysis in pre-calc 1, but instead of talking about the slope or talk about how it's increasing or decreasing, we were talking about function values centered around their zeros. That's what we did back in pre-calc 1. It's a similar idea, but we're doing this with derivatives instead of functions, so we're talking about change instead of actual function heights. All right, so let me redraw that line from above. I'm going to skip the colors. We got our -3 as a test point. We got our -2 as a critical number. We got our 0 as a test point. We got our 10 as our critical number. We got our 11 as a test point. So here's what we have got out of this. Until we hit the critical number of -2, we were increasing. Until we hit the -2, we're increasing. What does that look like? It looks like we're doing this. This is what increasing looks like. It doesn't have to be in a curve. You can draw this as a straight line if you want to, but we tend to be dealing with polynomials, so they tend to bend. So until we hit the -2, we are increasing. But then, after the -2 critical number in the region where the 0 is, we saw that that derivative was negative, so it's decreasing. That means from the -2 to the 10, we're going down like this. We're decreasing. And again, it might be a straight line, it might be bending, it might bend quicker, it doesn't matter. But then, to the right of the 10, specifically at the 11, or the 10.5 or the 12 or a million or whatever, we're increasing. So from 10 on, these are like walls, we are increasing. So it's back to going up and bending. These do not have to be drawn, but I think it's another visual flair that helps. So around the -2, here's the point -2, we're increasing and then we're decreasing, so that looks like a max. That's the red and the blue. We're increasing and then decreasing around the -2, which means it has to be a max. Around the 10, if here's the point for the 10, we were going down and then we were going up. Oh, I drew that point just a little too high. It should be here. We're going down and then we're going up. That looks like a min because it's the lowest point. I didn't have to go through all of this specific. It occurs if it's a positive derivative on the left and a negative on the right, or a negative on the left or positive on the right. I used visual cues to help make that analysis because it's clearly if you go up then down, you're going to have a max. If you go down and then up, you're going to have a min. And those critical numbers are supposed to be at those, well, critical points, the max or the min, unless it's just some weird case. Like if you were to increase and then increase, that wouldn't be a max. If you were to decrease and then decrease, that's increase, increase, that's not a max. Decrease, decrease, that's not a min. Increase, decrease, that's a max. Decrease, increase, that's a min. Okay. Now I want to get rid of what I just wrote, just that part. because I'm going to need that space for graphing. So we were supposed to graph the function. We have now identified the specific extrema. We have a local max at -2 and a local min at +10. So we have a local or relative max located at x equals -2. And we have a relative min. I don't know why I squished it together so much that time. Located at x equals 10. We don't know the heights though. What are the heights? We need f of x. The function tells us the actual heights. So if we go back to the original function, x cubed minus 12x squared minus 60x plus 36, let's just pull out a graphing calculator for the sake of time. Hello? I was kind of hoping that that was going to fix itself eventually. Hopefully this works. So we got -2 cubed. That looks okay, I guess. Minus 12 times -2 squared minus 60 times -2 plus 36. Let me make sure I've got everything typed correctly. -2 cubed minus 12 times -2 squared minus 60 times -2. That looks good. We hit enter and we get 100. So f of -2 is 100. You do need to know the actual locations of those points, not just where they're located at, but what they are. Then next, let's do f of 10. So f of -2, that was our max. So this should be the maximum value. We'll label that in a minute. Now let's do the 10. Let's go back to our calculator. Let's do 10 cubed minus 12 times 10 squared minus 6 times 10 plus 36. That looks good, doesn't it? 10 cubed minus 12 times 10 squared minus 6 times 10. Then the plus 36. I think I have a typo on my notes. I have a wrong number there. I just want to make sure this is right. Yeah, that's right. Okay. I just need to scratch out that number on my notes. No big deal. Okay. So f of 10 is -224. Now you might think that, oh, okay, well, if this was supposed to be the minimum for some reason, let's say this was supposed to be the min and this was supposed to be the max, you might think, well, that makes no sense. Why would the max have a smaller number than the min? Because local extrema are only talking about right around them. You can have maxima that are smaller than minimum when you're talking about local extrema. Anyways, the 100 and the 224 are the actual outputs. So the relative max is 100, and the relative min is -224. So there's no disassociation for this one, but it could have happened. That's something to be careful with. You don't want to overthink it. All right, so now that we know where these peaks and valleys are, let's draw them that way. Let me zoom out just to give myself a little more space to make a good graph. There we go. So our x values aren't varying too much. We got a -2 and a 10, but the y values are definitely varying wildly between 100 and -224. So let me put my, let's just say the 100 is here, and let's say our negative, no, I need to make that a little lower for scale. Let's say the 100 was here, and the -224 was here. Then let's say the x equals -2 is right here, and the x equals 10 is over here. I just don't want to have 50 million hash marks. I gotta sneeze. I'm gonna try and mute this in time. All right, I got it. All right, so -2, 100, that's left to 100. There is the relative max. And I'm actually gonna write the word max by it as a helpful reminder, as a very helpful reminder. Then the other point was the 10, -224, so that's over here, right? 10 down 224, and I'm gonna write min by it as a helpful reminder. So now, imagine that you had your nose to these 2 points. So this little green box, which I will erase in a minute, this is where your nose is and all you can see. If that's a maximum, that means around that point, it has to look like this. It has to be going down of both sides around it. It has to go from increasing and decreasing. There's nothing else that that curve could do in that region. So what you do is you just draw a little segment right around it, demonstrating that. Because that has to be a max, it has to look like that in that region. And I've kind of done that a little ugly, but I'll make it better. That's what it has to look like in that region. It might be tighter, it might be wider, but it has to look something like that for it to be a local max. There's nothing else it could be. On the contrary, the minimum, again, if you nose to the board just around this point, because it's a minimum, it has to be going up everywhere around it. So what we do is we draw it going up on both sides. And again, the wideness or narrowness of yours will just be based on how you want to make it. Now again, back in pre-calc, we would know some zeros. We could set the function equal to 0, and you still could arguably do that here, but trust me, the numbers are not pretty. They're not going to be whole numbers, at least not all of them. I can guarantee that. But we don't need it. We don't necessarily need to know the zeros in calculus. We tend to be much more interested in the extrema, the maxes and the mins, the best and or worst. Well, these are the only extrema, so what that says is there's no other time where it's not like if there's a point here, there's no way it could be going up on both ends. If there was a point here, there's no way it could be going down on both ends because we have found all of the locations that can happen. So all we do is just try and connect everything and keep moving in the directions that you see. So we're going down from this max, you're going up from that min, so it's probably going to look something like this. That's not the best. Something like this. That's not the best. Not so much a line. I want to flatten out this a little. Let me just flatten that out. That's about what it should look like between those two. The steepness of this, sketching this by hand, how steep that is, I'm not worried about that. What I'm worried about is that it doesn't look like this. You don't have extra hills and valleys. And it doesn't even have to be a ridiculous amount. It just can't look like that because then you've got an extra hill and a valley, which they don't exist. We found all of the ones. So it's got to look something like that between them. To the left of the max, it's going down. You can't do this because that would imply another extrema. You can't bend or turn around at any point. You just got to keep going down, 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 forever and ever. And to the right of the minimum, you can't turn back around at any point. You can't do this because then you've got an extra extrema. So you just keep going in that direction. Up, 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 up. And there's our sketch. That's the most detail I would need to see if this was paper pencil. I don't need to know the locations of this this, and this 0. I don't need to know those locations necessarily for what we do in calculus. I'm not saying they're not important values. I'm not saying that maybe your boss wouldn't need them for some reason. I'm just saying that in here, it tends to be less important. We're just finding a new way to graph things. Again, what's important is that you don't have extra zigzags in other regions, other peaks and valleys that don't exist. You're finding the maximum number of peaks. And if you remember back in pre-calc, we talked about the maximum number of turning points. It was always 1 less than the degree. This polynomial was of a degree 3. There are 2 turning points. Turning points are extrema. Kind of just a little reminder. What's happening? Turning points are the extrema. So there's 2 turning points in this graph, which is 1 less than the degree. So that's good. If I drew this and there were 4 turning points or even 3 turning points, we've got too many. It would not be correct. So that is how we go about graphing polynomials in a calculus concept. Another thing that we can check is the leading coefficient test, LCT leading coefficient test. This function was approximately, where's my squiggle? There we go. Just looking at the leading term, which governs the growth at the ends, was x cubed. X cubed, that little caret just means x cubed, which x cubed graphs go down on the left and up on the right with a positive. And that's exactly what happened here. It went down on the left and up on the right. So this was using the first derivative test to find our extrema and ultimately make a sketch of a graph. Again, if this function had zeros, they were easy to find by factoring, you could do it. This is not easy to factor, I can guarantee that. You would definitely need to list all the possible rational zeros, which are the factors of 36. Do synthetic division to see which one makes the function 0, and I'm not even going to guarantee that any of them do. Let's pull out a calculator and just see. I'm kind of curious if this will work. Let's see what this looks like. X to the third minus 12x squared minus 60x plus 36. This will be the last thing we do. It looks like just the outline of my TI-83 is missing. And we can hardly see anything because this function is dealing with pretty large numbers, so we should probably zoom out, or at least make the heights different. I'm going to leave the x scale the same, except I'm going to go to 11. The y scale, let's make the y minimum negative 500, and the y maximum, let's make that 200. And that did not go down enough. So window, maybe I had a typo somewhere. You know what, my 764 was right. Why did I get a different number earlier? That's all I got to change. I knew that 764 is right. What did I do wrong earlier? Negative 10 or 10 cubed. Oh, I know what I did wrong. I had a double negative situation right here that I didn't account for. No, I didn't. That's not right. Did I do 60? I did 6. Look at that. That's a 6, not a 60. It was negative 764. Okay, so let me just correct that in my notes real quick, that this should be negative 764. As should this. As should this. Sorry about that tiny little arithmetic error, but the point is still here. Look at the graph that we sketched out and look at the graph that we got. As I said, the steepness here, now because I was scaling this to be about 2.5 times that distance, this should be a lot further. I want to redraw that graph to emphasize that. I'm so sorry. So here's my -2, here's my 100, here's my negative 764, and here's my 10. So we had this point and this point. Then we do our basic, oh, they were maxes and mins. Then we connect them. Then we continue the trends on the outsides. Now that looks a little better to the graph. And again, that's just because I had my graph scaled poorly because I had a wrong value because I missed a 0 when I typed my calculator. I know I typed 60. What happened was this thing, if I click too quick, it doesn't register. So that was my bad. I'm sorry. I'm going to keep apologizing. Sorry. And I'm not much of one to apologize. So that graph looks pretty good for a sketch, considering we didn't use technology at all to make that, besides finding our error. Trace. If you type in -2, you can now see that. If you type in +10, you can see that. Now the point of this was trying to find the zeros, trying to find the locations here. This looks like -1, 2, 3, -4. If I type -4, what do I get? 20. It's close, but it's not 0. And if I try and hone in on that, it's going to be some ridiculous value. You might think 0 works. And that's 36. It's not quite there. You might think it's 0.1. 0.1. See, there it was. I clicked something and it didn't register. 29. Not quite. I mean, you can't find these zeros analytically, even with the techniques we taught you in pre-calc. But again, I didn't want the zeros. I didn't ask for that. They're generally not as interesting at a calculus level because we have, in my opinion, a better way of graphing, because in calculus, we tend to be more interested in the peaks and valleys. So I'm going to go ahead and call it a day there with a few minutes left after making that error. I was going to say one more thing, but we can say it next time. We have not finished 3.1. We have not come close to finishing 3.1. We will do a lot more next time. But for now, don't focus on chapter 3. I'm not even giving you a due date on 3.1 yet. So don't sweat that. I need to give you a due date for 2.4. When will the dates for the homework in chapter 2's integrated quiz be logged? The integrated quizzes have no due dates. Those are assignments that you just have to do before the homework, so that way anything that you are really, really efficient at, you don't have to do those extra problems. So again, there are never going to be due dates for integrated quizzes, so you just have to do that before you have access to any other homework. The one due date you're missing right now is 2.4. That crashed. I'm sorry, not 2.2, 2.3 is going to be due. And a week from today would be the 18th. I know you're going to be focusing on your test, so I'm going to give you extra time. I'm going to give you till the 22nd. So that's going to be due on 6/22. So those two assignments should be visible. You don't have access to... You can see those quizzes, right? It's just a matter of you have to do it, and then the flags for your chapter 2 homework will go away. And if that doesn't happen, okay, so the first thing I do as soon as this class ends, I will make that quiz available. So that way you have access to the homeworks. Then I will continue building your review. So again, your review should be available no later than 5 p.m., hopefully by 3 p.m. I don't think it's going to take me more than, I got to eat lunch. Between that and working on finishing the test, finishing the review, I should have all that done by 3. Again, if you don't see it by 3, definitely by 5. This video should be up soon. Hope you'll have a good one. Work hard, study hard, do problems again. 2.2 is due on the 16th. I hit my phone looking at something if you heard that. 2.2 is due on the 16th. 2.3 is due on the 22nd. So 2.2 was done a decent amount before the testing and everything, so I don't mind having that due on the 16th. And that 22nd, that's a Monday, 23rd. 23rd, good Lord, all over the place. 2.2, 16th, 2.3, 23rd. They'll be accurate in my math lab, I promise. All right, if you have any questions or confusion, email me. Besides that, have a good day.